Morning to all of you. We will continue with our discussion on electrostatics. In the last lecture, we had started to discuss electrostatic potential and potential energy. So, we started to discuss electrostatic potential and energy, and electrostatic potential. Electrostatic potential energy is the work done by an external agent to move a charge from one point to another point. So, we had derived that the potential energy of a pair of particles of a pair of point charges q and q is V u is equal to q by 4 pi epsilon 0 r, where this is the charge small capital Q, the small charge q, and this distance is r. So, that defines the potential energy of a pair of point charges. If you have multiple point charges, for example, potential energy of a system of charges, u will be equal to, say if you have 3 charges q 1 q 2 by 4 pi epsilon 0 r 1 2 plus q 1 q 3 by 4 pi epsilon 0 r 1 3 plus q 2 q 3 by 4 pi epsilon 0 r 2 3. So, essentially you have one charge q 1 here, another charge q 2, say another charge q 3. So, the potential energy is essentially defined by the separation between this is r 1 2, this is r 1 3, and this is r 2 3. So, we have the potential energy for a system of charges, and I must mention, as I mentioned last time, that this potential energy is independent of the sequence in which you are assembling the charges. So, it does not matter whether you bring q 1 first and then q 2 and q 3, or you bring q 2 first and then q 1 and q 3, it is independent of the sequence of assembling of the charge distribution. And also remember that this is an energy that is contained in the complete system of charges. We then defined the electrostatic potential as the work done in bringing a unit charge from infinity to that point. So, for example, the potential for a point charge q will be V of r is equal to q by 4 pi epsilon 0 r, where q is some charge here and r is the distance from here from the charge, and that is the potential at this point the point at distance r from the point charge. That is the actually the work done in bringing a unit charge from infinity to this point here. And remember that V of r is a scalar quantity. I will show you later on that V of r and the electric field, corresponding electric field, are related. In fact, I must write a vector here. The potential at any point and the electric field at that point are related to each other. Sometimes it is easy to calculate the potential, and from the potential to calculate the electric field, and we will see some examples a little later. I also introduced the unit of potential it's volt. So, 1 volt is equal to 1 joule per coulomb. That is the work done on energy in moving one charge from infinity to that point. At this point I might like to mention that there is a unit of energy which is used in many places. Called the electron volt. Abbreviated as EV. So, 1 electron volt is equal to the charge of 1 electron into 1 volt, which is 1.6 10 to the minus 19 joules. So, that is a unit of energy. It is the energy required to move a charge of 1 electron across a potential difference of 1 volt. I also can relate the work done by an external force in moving unit charge from a point R I to R F is W is equal to V at R F minus V at R I. So, for a point charge, W will be equal to Q by 4 pi epsilon 0 1 by R F minus 1 by R I. So, the work done in moving a charge from one point to another point depends on the potential difference between these 2 points, and that is a typical relationship which tells you the work done for moving a unit charge is the difference of potentials between these 2 points. Potentials follow a superposition principle. So, if you have a number of charges q1, q2, q3 etcetera, and if you had a point here. So, if I call this distance r1, this distance r2, this distance r3. So, the total potential at this point at a point P is actually equal to q1 by 4 pi epsilon 0 r1 plus q2 by 4 pi epsilon 0 r2 plus q3 by 4 pi epsilon 0 r3. So, in general this is actually qi by 4 pi epsilon 0 ri. And if you have a distribution of charges, so if I have a volume with some distribution of charges, I can take a infinitesimal volume here with a charge dq, and I want to calculate the potential at this point r at a distance r from the origin. This is the origin, and if I call this r prime, V at r is actually 1 by 4 pi epsilon 0 integral dq by r prime. So, r prime is the distance of this point from the elementary charge dq, and I integrate over the entire volume or the surface or the line to get the total potential at that point. So, we can use the superposition principle to obtain the total potential at any point in the presence of multiple charges. So, now I want to discuss some examples to show you how I can calculate the potential. So, first let us start with the first example, potential of a charged conducting sphere. So, I have a sphere which is a conducting sphere, and it has an excess charge q put on it, let r be the radius of the conductor. So, we have actually shown before that the electric field produced by a conducting sphere, charged conducting sphere, is the same as if the entire charge was situated on at the center of the sphere. As far as outside regions are concerned, inside the conductor the electric field is 0. So, actually we can get the electric field here as q by 4 pi epsilon 0 r square into r cap. This is for r greater than r, which is equal to 0 for r less than r. No electric field inside the conductor and an electric field of q r cap by 4 pi epsilon 0 r square. So, r is the distance of any point from here. So, I can calculate the potential at this point. V r is equal to integral infinity to r f external dot dr, which is equal to minus q by 4 pi epsilon 0 integral dr by r square infinity to r, which is actually equal to q by 4 pi epsilon 0 r. This is for r greater than r, because the electric field which I am using here in this integration is the electric field for a point lying outside the sphere. So, that is the potential as far as outside points are concerned, and the potential is exactly the same as if the entire charge was concentrated at the center. So, I can calculate what is the potential at the surface of the sphere, which is equal to q by 4 pi epsilon 0 r. This is at r is equal to r. So, the potential keeps on changing until I reach the surface of the conductor, and the variation is given by q by 4 pi epsilon 0 r. Now, inside the conductor there is no electric field. So, I do not have to do any work in moving a charge inside the conductor from the surface to any other point inside the conductor, which means that the potential inside the conductor must be the same as at the surface of the conductor. Remember, potential is related to the work done in moving a charge. So, because there is no electric field within the conductor, I do not have to do any work in moving the charge anywhere within the conductor, which means that the potential inside the conductor must be the same as this. So, what I see is, first of all, the entire conductor is at the same potential. So, conductor forms an equipotential surface. It is a surface where the potential remains constant, and so if I were to draw the potential as a function of position. So, if this is my sphere carrying a charge, so let me try to draw a figure here which shows B as a function of r. So, this is the radius as a position, as a function of position. If I plot, you see that as I come, suppose the charge is positive, as I come closer, you look at the potential distribution here 1 by r. So, as I come closer to the sphere, small r decreases, and so the potential increases. So, the potential increases 1 by r from on here and here. Then inside the conductor there is no change in potential. So, as I move away from the sphere, the potential drops as 1 by r, and inside the conductor the potential remains constant. So, this is actually q by 4 pi epsilon 0 r. So, inside the conductor the potential is constant, but I already have calculated before the electric field as a function of position, electric field. So, let me look at the same boundary here. You know that electric field goes as 1 by r square, here the electric field goes as 1 by r square. So, it goes faster than 1 by r, but and it rises faster like this, and then the electric field becomes 0 inside the conductor, and then again it drops fast. So, you can see that the electric field decreases faster as a function of r. Inside the conductor the electric field is 0, inside the conductor the potential remains constant. So, please note here that I can have regions where the electric field is 0, but the potential is not 0, the potential will remain constant in that region. So, a conductor is an equipotential surface. So, let me calculate some numbers here, let me put some actual values and calculate. So, let me take a sphere of radius r is equal to 10 centimeter, which is 0.1 meters. So, this is a conducting sphere. Okay. Let me assume that we have a charge of 1 nanocoulomb 10 to the minus 9 coulomb placed on this sphere. So, what is the potential on the sphere? It is q by 4 pi epsilon 0 r, which is equal to 10 to the minus 9 into 1 by 4 pi epsilon 0 is 9 10 to the power 9 divided by 0.1, which is equal to 90 volts. So, if you take a sphere of radius 0.1 meters and put a charge of 1 nanocoulomb on the sphere gets a potential of 90 volts. It essentially means that you need to spend energy to bring a charge from infinity to this point if the charge is positive. So, what is the electric field? Electric field on the surface is actually, as you can see here, electric field varies as 1 by r square, potential varies as 1 by r. So, the electric field on the sphere, surface of the sphere, must be q by 4 pi epsilon 0 r square and radially directed. So, this is equal to V by r, which is equal to 90 by 0.1, which is equal to 900 volts per meter. So, on the surface of the electric field, on the surface of this spherical conductor, you have an electric field which is pointing like this of 900 volts per meter. It is pointing like this here, pointing like this. If the surface charge is, if the charge is positive, positive q. If the charge is positive, electric field is pointing away, and the inside the conductor, the potential remains constant. Now, I must mention here a certain aspect that happens in nature, and that is if you look at electric fields in air, if the electric field becomes stronger and stronger, the electric field can knock off electrons from the atoms, and so it creates a breakdown. You can see a spark taking place in air, and at the typical conditions, the maximum electric field in air so that there is no breakdown, E max is equal to 3 to 10 to the power 6 volts per meter. 3 million volts per meter is the maximum electric field you can have. If you try to generate an electric field beyond this point, then there will be a breakdown, and the electric field will be so high that you will see a spark coming out of that conductor. So, you can see here that if you take a radius of 0.1 meters, the maximum potential of this conducting sphere V max is equal to E max into the radius of the sphere, which is 3 10 to the power 6 into 0.1, which is equal to 3 into 10 to the power 5 volts, which is written as 300 kilovolts. If you decrease the radius to r is equal to 1 centimeter, which is 0.01 meters, V max reduces by a factor of 10 and you get 30 kilovolts. So, you cannot have a conducting sphere of radius of 1 centimeter and raise it to a potential greater than 30 kilovolts, because if you try to increase the potential by charging more, the electric field becomes so intense that there will be a spark in air and the charges will get out from this spherical conductor. So, there is an upper limit to how much of charge you can put on the conductor. You can from here calculate for this radius what is the maximum charge that you can put on the spherical conductor. I would like to discuss another important example, and that is potential due to a dipole. Remember, in an earlier class we had discussed the electric field produced by a dipole. We had calculated the electric field along the axis and on the equatorial plane, and right now I want to calculate what is the potential of a dipole. So, let me draw the dipole here. So, this is minus q this is plus q. Remember the dipole moment is from minus q to plus q. So, I want to calculate the potential at this point. So, let this point be the center of the dipole, this distance let me call r, let me call this distance r1, let me call this distance r2, this is the point P. This distance is r from the center O to this point P is r, this distance from minus q to P is r2, from plus q to P is r1. So, remember potential satisfies superposition principle. So, V at P must be equal to potential at P due to plus q charge plus potential at P due to minus q charge. Now, because this distance is r1, the plus q charge produces a potential 4 pi epsilon 0 r1 and minus q produces minus q by 4 pi epsilon 0 r2. So, this is actually q by 4 pi epsilon 0 1 by r1 minus 1 by r2. Now, let me call this angle as theta. Now, you have all done geometry and calculated the relationship between the various lengths of a triangle. So, let me write down the equation here, r1 square is actually equal to r square plus. So, this distance was 2a, remember we had marked a dipole as two equal and negative equal and opposite charges separated by distance. So, 2a is the separation between the two charges. So, r square plus a square minus 2 ar cos theta and r2 square is equal to r square plus a square plus 2 ar cos theta. So, actually substituting this r1 and r2 in this equation, I can calculate the potential at any value, any point, if I know the distance of that point from the center and if I know the angle made by that line joining the center of the dipole to the point with the dipole axis. So, this formula can be used to calculate potential at any point, and please remember potential is a scalar quantity. So, I am just adding the quantities potential because of plus q plus potential because of minus q. Now, we had also introduced a point dipole where the dipole size is very small compared to distances. So, let me try to calculate an approximate expression for the potential when the distance r becomes very large compared to the size of the dipole. So, if r is much greater than a, I can make an expansion of this and obtain approximate expressions for r1 and r2. So, if you look at r1 square, let me write down r1 square again. So, r1 square is equal to r square plus a square minus 2 ar cos theta, which is equal to r square into 1 plus a square by r square minus 2a by r cos theta. So, r1 is approximately equal to r into 1 plus a square by r square minus 2a by r cos theta raised to the half square root. So, 1 by r1 is approximately equal to 1 by r into 1 plus a square by r square minus 2a by r cos theta raised to the minus half. I have just inverted. Now, if r is much greater than a, then I can approximate, actually these are exact relation, they are not approximate, they are exact. Now, I approximate. So, 1 by r into you know the binomial expansion here. So, I get 1 plus a by r into cos theta approximately. So, I have neglected terms of order a square by r square and greater. So, a square by r square, a cube by r cube, etc., all these things have been neglected in writing this approximation. So, 1 by r1 is approximately 1 by r into 1 plus a by r cos theta. Similarly, I can make an approximation for r2 square. So, r2 square was equal to r square plus a square plus 2 ar cos theta. So, I leave the exercise to you. So, you can show that 1 by r2 is approximately 1 by r into 1 minus a by r cos theta. So, 1 by r1 minus 1 by r2 is approximately equal to 2a by r cos theta. So, 1 by r1 was 1 by r plus a by r square cos theta r square, and 1 by r2 was 1 by r minus a by r square cos theta. So, when I subtract 1 by r2 from 1 by r1, I get this. So, I get a potential V at P is equal to q by 4 pi epsilon 0 into 2 a by r square into cos theta. Remember, we had defined the dipole moment, magnitude of dipole moment as q times 2 a. So, V of P is equal to P magnitude cos theta by 4 pi epsilon 0 r square. Now, let me look at the figure here. So, remember here, so this is the figure, let me draw here again. So, I had the dipole like this. So, this was P vector and theta is this vector, this angle. So, at this point I am calculating the potential. So, this is r cap and this is P vector and this is theta. So, what is P cos theta? P cos theta is nothing but P dot r cap. So, this is equal to P dot r cap by 4 pi epsilon 0 r square. So, let me write again here. So, if I had a dipole like this P, and if I take a point P at a distance r from the dipole, and this, if this angle is theta, then B at r is equal to q by 4 pi epsilon 0 sorry P dot r cap by 4 pi epsilon 0 r square. And this is valid for r much greater than a, which is what we have assumed in deriving this equation. So, two things you notice, that unlike a point charge where the potential varied as 1 by r, for a dipole the potential varies as 1 by r square. Remember, we had seen this same thing in the electric field case. The electric field of a point charge varies at 1 by r square, while the electric field of a dipole varied at 1 by r cube. So, the potential is decreasing as 1 by r square from the dipole, and also it depends on the angle theta. So, as you change theta and keep the distance of the point P constant, if I move along a point with r as the constant, then theta changes, r remains constant, but P dot r will change, and so the potential will change. So, the potential not only depends on the distance of the point from the dipole, but also the angle made by this line with the dipole axis. So, for example, so if I write in terms of theta, this is equal to P cos theta by 4 pi epsilon 0 r square. So, if you take theta is equal to 0, V of r along this line theta is equal to 0 is P by 4 pi epsilon 0 r square. Theta is equal to 0 is, this is P, this line, this is theta is equal to 0, and for theta is equal to pi, B of r minus P by and so this is, please remember, this is minus q, this is plus q. The dipole moment is a vector from minus q to plus q. So, the dipole moment is pointing like this, and so the potential on this side is positive, the potential on this side is negative, and for theta is equal to pi by 2, V of r is equal to 0. Pi by 2 is this line. So, along the equatorial plane the potential is 0. You can immediately understand this, because this point, any point on the equatorial plane is equally distant from the plus charge and the minus charge, and because the potential is the sum of potential produced by plus charge and the potential produced by minus charge, and the charges have equal magnitudes, the total potential on the axis is 0. So, the potential of a dipole goes as 1 by r square, and the potential also depends on the angle between the P vector and the position where you are calculating d. So, just for a summary, let me look at a third example. and that is I want to calculate potential of an infinite linear charge density. So, I have a line charge here. So, lambda is the line charge per unit length, and I want to calculate the potential at some point here. Okay. So, this distance is r. Now, remember we had calculated the electric field of a infinite line charge. So, let me recall, to calculate the electric field I take a Gaussian surface which is a cylinder of radius r. The electric field, by three symmetry arguments we said the electric field must be pointing away from the line charge. So, the electric field must be in this direction here, in this direction here, if the line charge is positive, and so we calculated the total flux. Total flux was 2 pi r into L, if the length of this is L, into electric field must be equal to the charge contained by epsilon 0. So, we get the electric field as lambda by 2 pi epsilon 0 r. This we have already seen, and electric field vector is r cap, where r cap is this direction. Now, the r cap is a vector along a direction which is along the line perpendicular to the drawn perpendicular to the line charge. So, at this point the r cap will be like this, at this point the r cap will be like this. So, that is the electric field. So, I can actually calculate the work done in bringing a charge from some point r a to r b. So, let me take a point here. So, this is a point at distance r a, this is a point at distance r b. So, this distance is r b. So, I want to calculate what is the work done. So, work done is equal to minus r a to r b lambda by 2 pi epsilon 0 r cap into dot product with r cap dr. So, which is equal to minus lambda by 2 pi epsilon 0 r a to r b dr by r, which is equal to lambda by 2 pi epsilon 0 log of r a by r b. Integral of 1 by r dr is actually log, and I have taken care of the sign by reversing the inside the log. So, the work done in bringing a charge from r a to r b is essentially lambda by 2 pi epsilon 0 r a by r b log. Now, you already see a problem here, and the problem is that if your reference point happens to be infinity, which means if I take r a to be infinity. So, this is the work done in bringing a charge from r a to r b. So, if I start from infinity, I see there is an infinity within the log, and there is a problem, and that problem is appearing because the line charge density itself is extending over infinite length. So, in such situation, in problems in which the charge distribution extends to infinity, which is of course not practical, because usually in practice all charge distributions are finite, but in mathematics we tend to use certain distributions in which the charge density is extending over infinity, for example, infinite line charge or infinite plane sheet, etc. And these are useful to calculate electric fields and potentials, but in such situations you will find an infinity of potential at infinite distances from the charge distribution. So, in these cases what we do is we change the reference point, and we say that instead of using reference point to be infinity, we will say that we will use the 0 potential at some r value. So, if I say, so let V is equal to 0 at r is equal to r a is equal to capital R, and we let the final point to be r. So, we will get V of r is equal to lambda by 2 pi epsilon 0 log capital R by small r. because potential is a relative quantity, it is like in gravitational potential, a potential at a certain height is measured with respect to potential, 0 potential on the earth surface. So, you can measure the potential differences between points, they will not depend on the origin of the reference. So, here what we have done is, because the potential tends to infinity, at infinity we have restricted and said that we will choose the 0 potential to be at a finite distance from the line charge distribution, and which I have chosen as capital R. So, you can see if you put small r is equal to capital R, log 1 is 0 and you get potential as 0. So, that is the origin of the potential. So, I brought this example just to indicate to you that there may be situations where the potential may be tending to infinity at far off distances, and so I may have to choose a different reference point for 0 potential. Now, I want to bring in some very interesting aspects, which is the equipotential surfaces. Now, we have earlier introduced the concept of electric field lines. So, we represent electric field distribution by electric field lines. So, these are lines of curved lines in which are such that the electric field at any point is directed along the tangent to that line, and the closer the lines are, the stronger the electric field is, the further they are, less the electric field is. We can similarly represent potential through what are called as equipotential surfaces. So, this is a graphical representation. So, what we do is we draw surfaces on which the potential remains constant. So, I take all those points for which the potential happens to be, say, V is equal to V1, look at all the points and join them and get a surface. Similarly, I take a surface corresponding to V is equal to V2, V is equal to V3 and so on. So, I draw surfaces which are such that all points on that surface are at a constant potential. So, these are all 3-dimensional surfaces, unlike electric field lines are lines and these are complete surfaces. So, also notice that since it is an equipotential surface, suppose the equipotential surface happens to be like this. So, the potential on all these points are exactly the same. So, I would have to do no work in moving along the potential equipotential, because the potential is the same. So, potential at this point and at this point are the same. So, I need not do any work in moving a charge from here to here. So, it implies that there can be no electric field component along the equipotential surface. So, electric field at every point must be perpendicular to the equipotential surface. Please look at this argument that if I had an equipotential surface, then all points on the surface have the same potential. So, the work done in moving a charge from one point of the surface to another point on the same surface must be 0, because they are at the same potential, and potential difference gives me the work done necessary to move a charge from one point to another point. So, because the potential is the same, there must be no electric field along the direction of motion. Whatever direction I choose, I move like this or like this or like this. In any direction, if I move on the surface, I would have to do no work in moving the charge, which means the electric field must be perpendicular like this. So, at this point it must be like this, if the surface is like this, it must be like this. So, electric field lines are always perpendicular to the equipotential surfaces, and this is very, very important. So, equipotential surfaces and electric field lines form are always perpendicular to each other. So, let me take an example of a point charge. So, suppose I take a point charge, here is the point charge q. So, remember, for a point charge the potential is q by 4 pi epsilon 0 r. So, if you take, so r is the distance from the point charge. So, if you take points which are at the same distance from the point charge, they will have the same potential. So, for example, at r is equal to r1, b must be b is equal to v1 is equal to q by 4 pi epsilon 0 r1. So, if you take a distance r1 from here, this all points on the sphere are equipotentials. Similarly, if you take r is equal to r2, v is equal to v2 is equal to q by 4 pi epsilon 0 r2. That is another sphere. That is another sphere. So, equipotentials for a point charge are spheres. I am drawing a circle in a 2-dimensional space, but you have to imagine this entire thing is rotated around the point charge here. So, if I rotate along any axis containing the point charge, this circles will become spheres, and all points on the sphere are at the equipotential. So, for a sphere of radius r1, the potential is V1 is equal to q by 4 pi epsilon 0 r1. So, this is an equipotential surface, that is an equipotential surface, and as you know, the electric field of a point charge is radial, is like this, and as you can see here, the electric field is always perpendicular to the equipotential surface. So, if the charge is positive, the arrows are pointing outwards, if the charge is negative, the arrows are pointing inwards. So, I leave it to you to calculate whether in this case, so R2 is greater than R1. What about if V2 is greater than V1 or V1 is greater than V2? So, please think over it, which potential is larger? Is the potential here larger than here, or the potential here is smaller than here? So, I leave this problem to you to think about it, to find out whether the potentials, the equipotential surface with a larger radius is at a smaller potential or a higher potential, if I have a charge, a positive charge here or a negative charge, for example. So, that is the equipotential for a point charge. If I had uniform electric field lines, so suppose I had electric field lines like this pointing in this direction, a uniform electric field, then equipotentials, as you can see, will be planes perpendicular to this line. So, if the electric field happens to be E is equal to E0 k cap, so let me call this as z direction. So, the electric field lines are along the z cap direction, k cap direction. So, the equipotentials must be parallel to the xy plane. So, this is x y. So, equipotentials are planes which are perpendicular to z axis here, because the electric field is along the z axis. So, I could show you some figures here, two figures which I will show you, showing the equipotentials for a point charge, and so this is the equipotential for a point charge. So, they are all spheres, and that is the center, which is the positive, which is the charge. This the black dot is the charge, and the equipotential surfaces are all spheres surrounding the charge. And as I have drawn in the earlier case, the electric field is radial like this. Okay, from the point charge. I have also plotted equipotentials for a dipole. This is calculated from the expression that we had written earlier, essentially this equation. So, you take different points. So, you calculate those points for which this potential remains constant. So, as I move the point, R1 and R2 must vary such that 1 by R1 minus 1 by R2 remains constant, and I can draw. So, these are equipotential surfaces, and as you can see here, these are actually surfaces. So, I can imagine the surface by rotating about this axis. So, the electric field lines will be perpendicular. So, for example, here the electric field will be like this, here the electric field will be like this, at this point the electric field will be like this, the electric field here will be like this, or everywhere it is perpendicular, it is like this. So, the direction of electric field will depend on will be perpendicular to all the equipotential surfaces. So, you can actually plot equipotential surfaces for different charge distributions by calculating electric field, by calculating the potential, and from there you can plot equipotential surfaces, and you can verify that electric field distribution is always at every point perpendicular to the equipotential surface. Now, a little while ago I mentioned that electric field and the potential are related to each other. So, let us try to derive an expression relating electric field and potential. So, I want to consider two adjacent equipotential surfaces. So, let me draw something like this. So, this is potential V naught and there is another surface here V naught plus delta V, V naught plus dV. So, these are two potentials which are very close to each other. So, V naught and V naught plus dV. So, as we know, electric field at this point will be perpendicular, it will be like this. This will be a direction of electric field, it has to be perpendicular to the tangent to this line. So, this must be like this, perpendicular. So, now I want to do the following. I have a charge here, a unit charge which I move like this in some direction. Let me call this dl vector. I move a direction making an angle theta with the electric field direction. So, what is the work done? By the external force in moving a unit charge from, let me call this point A, this point B, from point A to point B. So, remember these are equipotential surfaces, here the potential is V naught, here the potential is V naught plus dV. So, work done must be equal to V naught plus dV, the potential at B minus potential at A, which is equal to dV. Work done in moving a charge from A to B is potential at B minus potential at A, which is V naught plus dV minus V naught, which is dV. Now, I also know how to calculate work done for electric fields. So, work done is also given by minus E dot dl. E is the electric field. So, the force on the charge is E vector. So, I must apply a force which is opposite to the direction of electric vector, which is minus E, and I am moving a distance dl from here. And what is E dl minus E dl, which is nothing but minus E dl cos theta, and these two must be equal. So, what I get an expression I see that E dl cos theta is equal to minus dV. So, I can write. So, dV is the difference in potential between these 2 points, which is also given by minus E dl cos theta. So, I get the following expression that E cos theta is equal to minus del B by del L. L is the dl is the element of length, magnitude element of length, and I am moving dl vector is the length of the vector, dl is the magnitude of the element of length, and I am moving in a direction defined by cos theta. Theta is the angle between the electric vector and the direction dl. So, for example, if I so this is a general relationship. So, let me assume I have a figure like this. I have an x axis here and a y axis here. So, the equipotential happens to be like this. So, if I move from here to here along parallel to the x axis, so this is V naught, this is V naught plus dV. If I move parallel to the x axis, electric vector is like this. Then E cos theta is not, if this is theta, E cos theta is nothing but x component of electric vector. So, my movement dl now is along x axis, parallel to the x axis. So, dl will be along x axis and theta will be the angle between the E vector and the x axis. So, E cos theta is nothing but the x component of electric field, which is equal to minus del V by del x. I am writing partial derivative because the potential depends in general on all coordinates x, y and z. So, the electric field component along the x axis is nothing but minus del V by del x. Similarly, if I move along the parallel to the y axis, if I move like this, I can relate E y as minus del V by del y and E z is minus del V by del z. 3 useful relationships which relate the potential to the electric field. So, you can see here the rate of change of potential with respect to x axis with respect to x is the negative of the electric field component along x axis. The rate of change of V with respect to y with the negative of that is the electric field along the y axis, and del V by del Z is minus E Z. So, the 3 electric field components are related to the potential variation as a function of x, y, z. So, this is what I meant before. If I calculate the potential distribution as a function of x, y, z, I can from that expression calculate the electric field distribution. So, in many situations it is easy to calculate potential distribution because potential is a scalar quantity, and when I integrate it is much easier to integrate a scalar quantity. In the electric field case I must calculate Ex separately, Ey separately, Ez separately because electric field is a vector. So, let me show you an example of this calculation of electric field relationship. So, potential of a point charge. So, V of r we have already calculated is q by 4 pi epsilon 0 r, where q is here and r is the distance. So, if in terms of coordinates I can write that this is 4 pi epsilon 0 x square plus y square plus z square is per half, but this point has coordinates x, y, z, and this is the origin. So, let me write here x. So, this is x, y, and z. So, you can the distance small r is the distance from the origin, which is square root of x square plus y square plus z square. So, for example, I can get E x is equal to minus del v by del x, which is equal to minus q by 4 pi epsilon 0 into, you can differentiate this, x square plus y square plus z square raised per 3 by 2, there will be a minus half sign and there will be a sign of 2 x. Differential of x square plus y square plus z square is 2 x with respect to x, partial derivative with respect to x, and I get this equation which is equal to, so 2 factor goes off and I get q by 4 pi epsilon 0. So, let me write like this, x square plus y square plus z square into x by square root of x square plus y square plus z square. So, this is nothing but q by 4 pi epsilon 0 r square, and this is x by r. Similarly, you can calculate E y and E z, and from there I will show you that the total electric field is actually exactly what we had obtained before. Now, I want to close the lecture with a small problem. An electric dipole of moment P is equal to 10 k cap is located at the origin in free space. Calculate the potential at a point P with coordinates x p is equal to 0.5 meters, y p is equal to 0, z p is equal to 0.87 meters. So, I leave this problem to you. Please calculate the potential at this point P. So, you have a dipole located which is oriented along the z axis here, and you need to calculate what is the potential at this point.